Alright, so in the last video I hope I sold you on the fact that light isn't just a wave, but it's also a particle. We had our little peanut for the lowest energy light, and we had our little black tomato, then we had Mr. Blue. And again, when they hit, Mr. Blue makes a dent or makes a big noise. He's got more punch to him. It's the photon that's a high energy, like a UV light, just has more inherent energy to it. It's a quanta. You get it. So every time a photon of that blue light goes by, it's like an onion goes by, heading on its way to go hit something. So I thought I'd help with that, kind of illustrate why we get some electrons. Let's say in this lowest, I drew a new circle around this nucleus and said that's our lowest energy level for an electron. And I brought some of Mr. Red, his friends, by, and I want you to hear it as it hits the notepad, because light, now we understand, has this kind of particle-like property, like it's like a photon, like sandblasting a wall. So you say, well, what if I brought a lot of these? Can't they maybe initiate a energy change of this electron in this energy shell up to the highest one? Well, I can't, because watch the way it sounds when it hits. It doesn't matter if you bring a lot of them. It's like that doesn't have together enough energy in that photon. This one here, the orange, this red one, when it hits, it just doesn't have within the photon itself enough energy to kick sometimes the electron up to the highest orbital, let's say from N1 to N3. So you have to bring in somebody bigger as a provider of energy than this low energy light, because it doesn't matter that it brought all his friends. And maybe another way you could say it, it's like having ping pong balls. You don't really care if someone throws 100 of them at you. They're just individual ping pong balls. By themselves, they just don't have enough energy to hurt you. So there go the peanuts. Not enough. Mr. Red, you can't do it. So maybe we could use this one as an example. Maybe we could take this photon and have a lot of his friends come with them and pump, bump, 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 like it's hitting these electrons. But every time it hits, it just doesn't have enough energy. The next one hits, it doesn't have enough energy. Well, let's bring in Mr. Blue. So if I had that electron and I want to excite it, well, I'm bringing in Mr. Blue, and now it hits that electron, you might say, and he jumps, because he had that energy between this point and this point. You have to add a lot of energy, delta E, and he had it within himself, within that photon. You say, well, if you brought another onion, well, then you could advance another electron. It's kind of a particle thing, where this big old particle, you might say, the photon in the blue wavelength, hit, and that electron jumped all the way up to the N=3 orbital. I know it's silly to use peanuts and black tomatoes and an onion, but that hopefully helps you understand the particle-like property of light that we need to see when you look at these illustrations of an electron being advanced up by a certain photon or a certain wavelength of light. It has to have a certain punch to it. Now let's move to the other side, the electrons, because it's funny, electrons were thought of as particles only, but in 1910 to 1920, the view of that changed. The view of the electron changed. It went like something like this. And I don't know exact dates, so be gracious. But John Thomson and Robert Millikan discovered that an electron has a certain mass to charge ratio, and Millikan actually worked out the, charge, and from that you could figure out the mass also. But anyway, these were considered as particles. In fact, the name that Thomson came up with was corpuscles. But electron was considered like a particle, and the early models of the atom had that particle going around in a planetary model around the nucleus, like we said, and this was a Bohr model. But things weren't making any sense, because electrons, if they're particles going around the nucleus, should cascade down, and it didn't help that, Bohr proposed, well, they just, not only do they go round and round, they go around at certain orbits, like certain distances. That's where they are from the nucleus, and there was no reason for that. There was no theoretical reason. Enter de Broglie, French a chemist physicist who, for his doctoral thesis, proposed the following. Well, if electrons or photons were thought of as waves and now are particles, what about electrons? What if they're not just particles? What if they're also waves? So the electron went the other way. It was a particle, at least it was thought that only, but it became thought of by de Broglie as possible wave. So what I want you to do is just introduce to you a wave here. Now, what I've done is I've drawn 2 points. We'll call these the points at which the wave value goes back to 0 at the wall, like if you're holding it, and you plucked your string like on a guitar, and it develops a standing wave. Now you can have different forms. You can have a lower energy wave. You can have where it just has one blue node. That's the lowest energy. So you have these different energies sort of that come to being because you have what's kind of you have a sort of endpoint for each end. It's not an unlimited wave. It can't just go anywhere to the left and anywhere to the right. It has to come back to 0 at these points. When you do that, it starts to force those waves to have certain, I guess, shapes, you might say. Well, what de Broglie thought is, well, okay, the electron isn't along a line necessarily, but it is loving on a nucleus that has a positive charge. So what if we just take those 2 points, expressing the wave as, this is now going to be seen as the electron. It's not here, here, or here. It's not riding wave back and forth. Woof, it's there. It's woof, woof, woof. It's the electron disembodied. Well, if we considered that wave, we grab those 2 points and we wrap them around and tie them back together here, and this dashed line was this solid line right here. Then you'd still have those crest, trough, crest, but they'd be expressed around the nucleus. It was a crazy idea given to Albert Einstein, I guess, by some of the preceptors or the people who were giving him the de Broglie doctoral degree. And Einstein said, that's a major breakthrough. The way you look at an electron, instead of being a particle going round and round, it's just there, all there. And not only that, being confined, having to come back, it has to come back on itself at the same point and going in the same direction. You get certain waves. Not only do you have then wave nature that helps us a little bit to understand the electron, but certain waves. And that kind of leads us to then by Schrodinger, the fact that we would have certain waves at certain energies that look a certain way. They have a certain shape to them. You've heard it maybe like S orbitals are spherical, P orbital looks like a dumbbell. That's where this comes from. The fact that the electrons were considered as a wave and they're confined. They have to have a standing wave around the nucleus. Boom, you get all these particular looks as far as a wave or an orbital. And I'll finish with this because this is more the practical side. Whenever you see then, I hope from this point on, a 1s and a horizontal line, what you're really wanting to think of is that horizontal line represents an energy expressed by a wave or a wave function, the woof woof, where these 2 electrons are kind of disembodied and they are the wave. Now, we have by Pauli exclusion principle a wave, a spin up and a spin down. Just please know these arrows represent electrons. These arrows here represent electrons. And electrons, we talk as if they're in the wave. And there's always, by Pauli exclusion principle, 2 electrons that can occupy the same, you might say, wave. The S, we'll get to the quantum numbers later, but just think of S as telling you a lot about the shape. If it's S, it's spherical. If it's P, it's more of a dumbbell shape. But what's interesting, a lot of students in high school never see it in color. The 1s is different from the 2s, which is different from the 3s in this way. You see that there's red only. It has no node. But here, there's what's called a radial node. The wave value kind of crest, then it goes through a 0, and then it comes back to red in the trough. So you have more energy within this wave because it goes through that single node, radial node. Now you don't have with a 2p a radial node. There is never a point by going like whoomp whoomp out. You never cross through a different color. You say, well, wait, no, you do. If you go round this way, well, that's called angular. But if I just go out and back and forth from this center of the nucleus is represented here in black. And I apologize, I should have said these are all together on top of each other, but I've separated them so you can see them all. This radial node, it never changes from blue. But here it did, blue, red, blue, red, blue, red, whatever. But here it changes around the angle. We call that an angular node. So both of these have one node, the 2s and the 2p. That's why they're both considered a second shell wave. But they express their node in a different way. And for other reasons we won't get into, the p is just a little bit higher than the 2s. Last, the 3s would be higher than the 2pz, 2py. I'm just talking about dimensions here. And 2px, you have 3 of those that can be expressed orthogonal to each other. There's always 3p orbitals because they can be expressed in different sort of spatial spatial wave, but you can't do that with an S here. It's already, you can't have a different orientation to it. So there's only one of those. There's 3 of these. The 3S, we see it goes red, blue, red. So starting from the nucleus and going out in a certain radius, red, blue, red, blue, red, blue, red, blue, red. You see that radial WUMP node, higher energy than these because it has 2 nodes, one right here where it goes to 0 value and one right here. And that's my best as far as bringing high schoolers back into maybe an understanding of quantum mechanics, 20th century, now 21st century, because that was important, this idea of a wave and it being confined. Again, I do want to stress, the only reason I've separated these is so I can see them all. They're actually, this is the nucleus, one nucleus for all these waves. So they'll be back right on top of each other. We just separate them so you can see them. And then last, I need to apply it to a carbon. Let's say we had 6 electrons. We have all those waves now we've talked about. They always just by 2 by 2 go into the orbitals. So if there's a 1s, we put 2 in there. There's a 2s, it's lower than the 2p's, we put 2 in there. And when you have these orbitals that are just right at the same energy, degenerate, you split those electrons that spin up. You keep the other one in the other orbital, and you also have it spin up. You're going to see that's according to Hund's rule. All right, I'm going to stop there. This, I guess, video is probably more than 5 minutes long. Thank you. I hope that helps you understand the electrons and how we need to see them as waves that are confined around the nucleus, and therefore we get these particular orbitals or waves. And also a lot about that big old blue. If we wanted to take an electron and get them all the way from 1s to 3s, we better use something big as a photon that has a lot of energy. Use those UV light or X-ray. Thank you. Bye-bye.